Thank you. As our chair said, I am Serena Eley. I'm an assistant professor of physics at the Colorado School of Mines in the United States. And today I'll tell you about some of our work in understanding the effects of nanoparticle inclusions in superconductors. Okay, so in general, my research group studies the effects of disorder on the electromagnetic properties of superconductors and magnetic materials. More specifically, we look at vortex dynamics in superconductors and skyrmion dynamics in magnets. And the work that I'll tell you about today was performed in part by former undergraduate student Sarah Jones, who is now a graduate student at the University of Colorado Boulder. I would also like to thank my collaborators in this work, which includes Drs. Masashi Miura, Yoshida Kato Savale, and Dr. Roland Willa. Okay, so as you know, vortices are formed by the penetration of magnetic flux when the applied magnetic field lies in between the two critical fields, Hc1 and Hc2. And the problem with vortices is that they introduce dissipation that can decrease the critical current and cause energy loss and noise in superconducting quantum circuits. Vortices are moved by current-induced Lorentz forces and thermal energy, but thankfully can be immobilized by disorder. So here you can see a simplistic picture of what's going on. A defect can create an energetically favorable spot for a vortex to localize to minimize the energy of its core, which results in an effective energy barrier that must be surmounted for the vortex to move. So the defect landscape in a material defines an effective vortex pinning potential. So weak collective pinning theory describes how an individual point defect alone cannot immobilize a vortex. However, the collective action of many point defects can indeed immobilize a vortex. On the other hand, strong pinning theory describes how a large defect or a few larger defects acting alone can indeed exert sufficient force to pin a vortex. And some of the most successful efforts in modeling vortex dynamics in superconductors has been simulations based off of time-dependent Ginzburg-Landau theory. And there's a nice effort to do this at Argonne National Lab that's led by Andreas Glatz, who may or may not be connected virtually. I think he's noted as the chair of this session. To understand how our experimental results, to compare them to the results from time-dependent Ginzburg-Landau simulations, we work with collaborator Dr. Roland Willa, who is currently at the Karlsruhe Institute of Technology. He was formerly at Argonne National Labs. And as a quick summary, these simulations consider an array of defects that attract vortices by lowering the free energy of the vortex core when the core overlaps with the defects. And then this attractive vortex pinning potential can be tuned by tuning the size and the shape of the defects. So as a quick aside, we very recently published a perspective in the Journal of Applied Physics on challenges and opportunities in superconductor vortex physics. So if you're interested in vortex physics, then perhaps you'd find this article interesting. Okay, so it's known that incorporating nanoparticles into superconductors can boost JC and make it more robust to applied magnetic fields. So in this study, we wanted to look very specifically at how the field dependence of JC depends on the nanoparticle density and size, and then how our experimental results compared to recent results from strong pinning theory based off of these time-dependent Ginzburg-Landau simulations. And then lastly, we wanted to look at how the rate of thermally activated vortex motion also depends on the nanoparticle density and size. And then very quickly, I simply wanted to acknowledge a lot of past work that has been done on incorporating nanoparticle inclusions into superconductors in a way that actually results in an increase in JC without, that is, they're able to incorporate nanoparticles without destroying the inline superconducting matrix. Okay, so before I describe our samples, I want to very quickly mention that, of course, when you want to conduct a systematic study of the effects of one particular variable, in an ideal world, you would only change that variable. So we'd only have the nanoparticle density and size changing. However, this can be challenging to nearly impossible. So there are other parameters that are changing. We do understand the effects of some of these that are changing, but we try to do as systematic of a study as we could do. So our samples are YGD BCO films that were grown via metal organic deposition by collaborator Dr. Masashi Miura at Sekai University in Japan. And in this study, we considered a set of 8 different samples. The film thicknesses do change. We understand the effects of a changing film thickness. I don't have time to discuss that in this presentation, though feel free to ask me afterwards if you are interested. The nanoparticle size ranges from 12 to about 40 nanometers, and this is tuned by changing the growth conditions and the impurity type that's added to precursors. The nanoparticle density ranges from 2 to 100 by 10 to the 21 nanoparticles per meter cube, and this is tuned by tuning the volume percentage of impurities that are added to the growth precursors. This table here shows a summary of the samples that we considered in this study. I'd like to point out that in one of the samples, we have barium tin oxide nanoparticle inclusions. These are the largest ones that are present in the lowest densities. A few samples contain barium hafnium oxide inclusions. These are the smallest, and they're packed in at the highest densities. And then some other samples contain barium zirconium oxide nanoparticles. Additionally, we have a reference sample that does not include an impurity phase. So in the image that you see on the right, this is a transmission electron microscopy image showing a cross-section of one of the samples that contains barium hafnium oxide nanoparticles, which are most of the dark spots that you see here. We have identified 2 spots that represent Y2Cu2O5 precipitates. We call them 225 precipitates. These naturally form during the growth process. So they are present in all of these samples, including our reference sample. And they are present at densities that are significantly lower than the density of the impurity phase. Okay, then I won't talk about film thickness. So here, you see a plot of our data of JC versus the nanoparticle density in all of our samples, collected at 2 different magnetic fields, 0.3 and 1 Tesla, and 2 different temperatures, 40 Kelvin and 5 Kelvin. We measured JC in a magnetometer, where we can use the beam model to convert the magnetization to JC. What you should notice here is that JC does indeed increase with increasing nanoparticle density. And then it tends to flatten out such that we don't see a huge additional benefit in having a higher density of nanoparticles between this point here and here. However, note that our magnetic field tunes our vortex density such that at higher fields we may see the flattening out occur at higher nanoparticle densities. However, I don't have very many points in this range, so I don't have too much resolution to look at that. This plot was extracted from a paper by Dr. Roland Willa and Andreas Glatz that shows results from time-dependent Ginzburg-Landau simulations considering YBCO samples containing nanoparticle inclusions. And here you see JC versus the nanoparticle density collected at different magnetic fields. Notice that my x-axis is normalized differently from there, so we can't quite do a one-to-one comparison. They too expected increase in JC with increasing nanoparticle density. And then I just wanted to point out here that their simulations show that eventually there should be a decrease in JC with increasing nanoparticle density. There are a couple of reasons for this, and one of them is that when you get to high enough densities, your nanoparticles are close enough together that it becomes easier for vortices to hop between neighboring nanoparticles. Okay, so now this plot shows JC versus magnetic field normalized to HC2 that we collected in all of our samples. And don't worry right now about which sample's which. What I want to simply point out is that on this log-log plot, above self-field, we see linear behavior. And this linear behavior means that we have a power law relationship between JC and the applied magnetic field, and we call the power law exponent alpha. This has indeed been seen before. We've seen it before. Other studies have seen it before. But the goal of our study was really to look at how alpha depends on the nanoparticle density and size as systematically as we could. So before I show you those results, I wanted to quickly show you a plot extracted from this simulation paper that shows the results of simulations for JC versus magnetic field, and each of the curves are for different nanoparticle densities. They too expect this power law relationship between JC and the magnetic field, and they go a step further to make predictions for how alpha should change with nanoparticle density at low fields and at high fields. So now we extract alpha from the slope from the slope basically of a linear fit to our data out here, and produce a plot of alpha versus nanoparticle density. And what you can't see here, you can see it very clearly on my computer, but you can't see it on the screen here, is that we have a gray region here that shows you which samples are thinner. We end up having samples that are in like a bulk regime and then in a 2D regime. The 2D regime samples are about 300 nanometers thick. And those samples clearly show a decrease in alpha with increasing nanoparticle density. And the only thing that strays from this a bit is this is a sample that's in the bulk regime that wouldn't be shaded, and this sample's in the bulk regime that wouldn't be shaded. But then otherwise, all these samples in the 2D regime indeed show a decreasing alpha with increasing nanoparticle density. And then for comparison to simulation results, here we see alpha versus nanoparticle density, and qualitatively, the trends look very similar. More quantitatively, if we look at alpha at low nanoparticle densities, we see an alpha of about 0.65, which is very similar to what's predicted. And then at high densities, alpha is about 0.2, and they predict about 0.3. But again, our axes are normalized differently. Now this plot shows alpha versus nanoparticle size normalized to half the vortex core size, our coherence length. And again, what you cannot see on this projector is that our grayed out region is here, and these are our thinner samples, such that alpha increases roughly linearly with increasing nanoparticle size. And the only thing that really strays from that, well, this is our bulk regime sample. The only thing that really strays from that is our reference sample out here. For the reference sample, I simply plotted it at the position of the size of the 225 precipitates. This isn't entirely fair. All the samples contain these 225 precipitates. But I wanted to place this point on here so that you could see a comparison of what alpha is in the reference sample to the samples containing these impurity phase nanoparticles. So for the sake of applications, low alpha is going to be good. That means that JC is decreasing slower with increasing magnetic field. So when you look at this, you would say, okay, great. We want a high nanoparticle density, a high density of small nanoparticles. to produce low alpha. That's going to be best for applications. Okay, so then we wanted to test high magnetic field predictions. And before I show you our results, I want to show you what time-dependent Ginzburg-Landau theory predicts at high magnetic fields. And when I say high fields, in our lab, we can collect data up to about 7 Tesla in a standard quantum design magnetometer. So we went to the high magnetic field lab to collect measurements at higher fields than that. So here you see the results from simulations. This is JC versus magnetic field collected at various nanoparticle densities. And what I'd like you to notice is that you can see non-monotonic behavior here at high fields. They predict a small peak will occur when individual nanoparticles pin multiple vortices. So when a nanoparticle pins 2 vortices, a small peak will occur. If it pins 3 vortices, they expect another peak to occur. And the position of the peak will depend on the defect size. And they saw that this non-monotonic behavior corresponded to a change to a non-monotonic dependence of the pinning force on the magnetic field. And again, specifically when nanoparticles go from pinning one vortex to pinning multiple vortices. And then for details on the microscopics of the simulations, I was going to refer you to our session chair as noted in the book, under its glass. I don't know if he is connected, but this is a very interesting effect that had not previously been predicted. So here you can see our experimental results for JC versus magnetic field. And I'm only showing the results for 2 samples. The purple curve is for the reference sample, and the yellow curve is for the sample that contains barium hafnium oxide nanoparticles. These are the small ones at high densities. And then this plot shows JC versus magnetic field for the sample containing barium hafnium oxide nanoparticles at various temperatures ranging from 1.4 Kelvin to 40 Kelvin. And what you should notice is that we see no non-monotonic behavior, no high field peak. We collected these measurements up to 35 Tesla in a VSM at the High Magnetic Field Lab in Florida. And the peak, we would expect the peak to occur at about 10 Tesla based on the nanoparticle size. So we considered various reasons as to why we don't see this peak. The most likely reason is due to a spread in nanoparticle sizes. So when I tell you that the nanoparticles are a particular size, that's actually the average size. There's always a spread in sizes. And this histogram here shows you an example. This was a film that was not in this specific study. The average nanoparticle size is 8 nanometers, but it actually ranges from about 5 nanometers all the way up to 15 nanometers. And a spread in the nanoparticle size would cause a smearing in this peak effect, since the position of the peak depends on the nanoparticle size. So it's very likely that the effect is completely smeared out in our samples. So if any of you are materials growers and you grow samples that contain nanoparticles, if you are able to create a narrower distribution, I think this is a very interesting effect to look for that has not been experimentally observed yet. Okay, so the last thing that I'd like to show you is the effect of nanoparticle density and size on the vortex creep rate. But first I have a background slide on vortex creep. So let's say that our vortex is happily sitting in the energy barrier, in the energy well that is created by our nanoparticle. Due to thermal energy, it can hop out. And the dissipation that's released during this process can result in a decay in a persistent current over time. So basically, vortex creep is thermally activated vortex motion. And if you induce a current, it would result in a decay in this current over time. This also directly results in reducing JC, whether you're doing the measurements with transport measurements or magnetization. We measure creep through magnetization measurements. And to do this, first we establish the critical state, and then we repeatedly measure the magnetization over time. And we can observe the decay over time. The magnetization is proportional to the persistent current. We can extract the current using the Bean model. Then if you plot this on a log-log plot, we see linear behavior, such that to first order, the decay is power law. The accrete rate is parameterized by S and is defined as the logarithmic derivative of J versus time. So then we can extract creep from the slope. We repeat these measurements at various temperatures and fields. And then we can create a plot like this, showing creep versus temperature at a fixed field. And this yellow curve that you see here are the results for a 900 nanometer thick sample that contains the high density of barium hafnium oxide nanoparticles. So then before I do a comparison to other films, I'll quickly show you how we think about what's creating the shape of these curves. This equation here is the expected temperature dependence of the vortex accrete rate based off of what's called glassy and collective creep theories. U naught is the energy barrier if we have no driving force, that is no current. Mu is called the glassy exponent. The value of mu tells us something about the accrete regime. So we expect one value if we have hopping of single vortices. We expect another value if we have hopping of small versus large bundles of magnetic flux. Little t here is time, so it would be about an hour. And 1 over T naught is this effective hopping attempt frequency. So one thing that people typically notice when you first look at this plot is that as temperature goes to 0, S extrapolates out to a non-zero value, which is typically indicative of quantum creep. Then in this regime, U naught tends to be much higher than the second term of the denominator, such that S may increase roughly linearly with increasing temperature. And then in this regime, oftentimes the second term of the denominator is much greater than the first term, such that temperature cancels out and we see a plateau. Now, if you see a plateau, this is typically indicative of a vortex glass state. This is seen in YBCO single crystals. However, here we see a very clear dip, and non-monotonic S of T is it's not common to see. You'll see it in samples with columnar defects, but dipping down to accrete rates that are this low at such high temperatures near TC is very rare. It's something that we don't completely understand. We don't understand why nanoparticles create this. It would be nice if we understood this, because we could hopefully apply it to other materials and figure out how to lower the accrete rates as we approach TC. And then at higher temperatures, we enter the plastic flow regime. Okay, so now I've thrown on here 2 other curves. And sorry, I noticed the contrast here is terrible on this screen. But basically this curve here should be a different color than that. And it is for a sample that contains barium tin oxide nanoparticles, the larger ones. And then this curve is for the reference sample that contains no impurity phases. So what you should notice here is that a high density of small nanoparticles is very effective in lowering the vortex accrete rate at high temperatures. And then here we can see the data at 3 Tesla, and the trends remain the same. And again, I'm sorry that these colors look exactly the same on this projector, but basically, again, this is our reference sample. This is the sample that contains the larger barium tin oxide nanoparticles, and then the yellow is the one that contains a high density of small nanoparticles. So now, on this plot, you can see creep versus the nanoparticle density, and there should be some lines here connecting all the points that you can't see on this projector. This data is collected at 0.3 Tesla, and then this data at 1 Tesla. All the data was collected at a temperature of 5 Kelvin, and I'm plotting it at 5 Kelvin because that is a temperature at which the film thickness should not affect the vortex accrete rate. So in general, there's a bit of scatter, but you can see that creep decreases with increasing nanoparticle density. And then this plot shows creep versus normalized nanoparticle size for 2 different magnetic fields. Open symbols are at 1 Tesla, closed symbols at 0.3 Tesla. And again, there should be some shading here that shows our 2D regime, but in general, it looks as if the accrete rate increases roughly linearly with increasing nanoparticle size. And the only thing that really strays from this is, again, these are just the points for our reference sample. That does not include the impurity phase nanoparticles. So, high creep is bad for applications. We want slow creep, so yet again we see that a high density of small nanoparticles would be ideal for applications. And then we do not, to my knowledge, we do not have direct comparisons that we can do to predictions from strong pinning theory. Okay, so the last thing that I wanted to show you was that we noticed some qualitative similarities between the dependencies for alpha and the dependencies for creep. And again, with the resolution of this projector, it's very challenging to see, but you can see here, we would have a grayed out region here, that alpha, the shape of alpha versus nanoparticle density, and the shape of creep versus nanoparticle density is very similar. There should be a line connecting all of this. And then, for our data showing alpha versus nanoparticle size and creep versus nanoparticle size, the shapes qualitatively look very similar. So in conclusion, we have looked at the effect of nanoparticle size and density on the vortex accrete rate and JC. We found a power law relationship between magnetic field and JC, and then looked specifically at how the power law exponent depended on the nanoparticle size and density. And in general, our results were consistent with results from recent time-dependent Ginzburg-Landau simulations. For the sake of applications, we found that a high density of small nanoparticles is favorable, and we found qualitative similarities between creep, the dependence of creep on nanoparticle size and density, and that of alpha. And then we did not see peaks at high magnetic fields that would be expected when individual nanoparticles trap more than one vortex. This is unresolved. Again, if you are a grower that can create monodispersed nanoparticles in a film, this would be a very interesting effect to look for. So thanks a lot for your time.
How and why did you decide to use barium hafnium oxide as nanoparticle inclusions? Are there any alternatives?
Yeah, so, barium hafnium oxide nanoparticles, so Masashi is able to grow them in very small at very high densities without destroying the inline superconducting matrix. So they have very nice lattice matching between the superconducting matrix and themselves. Whereas with like barium tin, which are larger, he really can't put them in at very high densities because he does end up getting some strain that can affect TC. So with all of these, which I didn't mention, TC actually does not end up changing.
I wonder, in the magnetization measurement, have you ever seen any flux jump or?
That's a great question.
Because you should see, I think.
No, not with YBCO. So we have, it's funny, with the YBCO samples, actually even at 400 millikelvin, we don't see flux
very
jumps.
slow.
We don't see them at all. In niobium-based samples, we'll see flux jumps below 4 Kelvin. And then we tried a mercury-based, like a highly anisotropic mercury-based film at 400 millikelvin. And we did see a lot of flux jumps, but we can get rid of them by sweeping extremely slowly.
And can I ask another
course.
question? I wonder, so I love this work. As an opinion, the number of nanoparticle as a size and number, which value is the optimum value?
So what we see from here is that including so you can't have like you wouldn't want a high density of big ones. You would greatly reduce your superconducting volume. So originally when we started this study, it was actually like 2007 or sorry, not 2007, I'm not that old, 2017. And we were trying to figure out if it was better to have like a low density of the bigger nanoparticles, which would end up then trapping multiple vortices, or a higher density of the small ones. And
I mean, I couldn't see about that information. Maybe because you increase the number of nanoparticle, and after after specific value, the critical current density decreases. And if you increase the diameter of nanoparticle and also decrease. So I think there should
So if you
be a very
increase the
specific number
diameter
and ratio.
and if you increase the diameter and then you increase the density, there are some material science issues that happen. So you start to see decreases in TC. It can be because of strain that's created. It can also be because you're greatly reducing your superconducting volume.
Yeah.
So finding that balance is kind of challenging. And for both, I guess, intrinsic reasons as well as like more extrinsic practical reasons, incorporating these smaller nanoparticles seems to be best. Also through simulations, they seem to find a kind of ideal nanoparticle size versus the coherence length.
Yeah.
So this nicely applies to YBCO samples that have small coherence lengths of about 2 nanometers at 0 temperature, increases with temperature, but in the lower TC materials where your coherence length is quite large, you can picture that you can't end up incorporating nanoparticles that are the size of a very large coherence length.
Yeah. Thank you.